our final topic for the semester is the divergence theorem. And what we've been doing so far, there's been a common theme about these pretty powerful theorems like Green's theorem, Stokes' theorem, and now we'll see the divergence theorem, is what it does is it takes a region and it relates an integral over the region to an integral over the boundary, right? And so you can use kind of either integrating over the boundary or integrating over the region itself as, you pick the easiest one for the given setting. Like we saw with Stokes' theorem, you could have a surface that's arbitrarily complicated. But if we know how to parameterize and handle the boundary, then the integration is not too bad, right? And so the divergence theorem is another example of this, where there is an equivalence between an integral over some region and then a boundary of this region. And so now, and both with like Green's theorem and Stokes' theorem, what we were looking at was the boundary is a curve, right? It was either, so for Green's theorem, we had that the boundary was a curve, and then we had some planar region, right? D and boundary curve C. All of this lived inside R2, right? This was all in the XY plane. For Stokes' theorem, we had still that our boundary was some curve C, but this had to be in three-dimensional space because we were looking at a surface, right? Maybe something like this. And this was in kind of 3D space here, like X, Y, Z, right? And now the divergence theorem will still be in 3D space, but now the boundary is going to be a surface. And so we have some solid here, like including the inside, and the boundary, we'll call this region E, and then the boundary is a surface, or sorry, the surface is the boundary of this solid, right? And so we'll look at how can we relate an integral for the interior of this three-dimensional solid to the boundary, which is a closed surface, right? So let's look at a statement of the divergence theorem. So let's let S be a piecewise smooth surface enclosing solid E. And let's say S is oriented outward. And then we also have F to be some vector field. We can say F equals PQ R here, right? Okay. And we have, let's draw what we're looking at here. We have some solid, some piecewise smooth surface enclosing this solid. So maybe here this kind of parallelepiped that I'm drawing can be this, this piecewise smooth surface, right? So this is S, and then E is everything inside of it. So you can imagine this being not like a hollow block, but a solid block, right? And so the interior is E. And here's what the divergence theorem says. Now, notice we also have some vector field. Maybe I'll indicate this vector field in blue. And I'll just kind of represent this vector field looking like a radially outward vector field, but we know this is an arbitrary vector field, right? And so here's our vector field F. And this vector field F is over a solid E, and where the boundary of E is this surface S that's enclosing this region. The divergence theorem says, well, it has to do with the divergence, that the divergence, if you integrate the divergence of the vector field over this solid E, this is the same as the flux integral or the vector surface integral of the boundary. So again, what the divergence theorem is saying is if you take the divergence of a vector field over a solid and you integrate this, right? Remember, the divergence of F is a scalar function. So this is truly just like a standard triple integral that we're used to here. The divergence theorem is saying that the integral of the divergence over this solid is the same as the flux of the vector field traveling through the solid, or through the boundary surface S. And this makes sense intuitively, because what is the divergence measuring? The divergence is measuring the outflowingness, right? And so it's how much is flowing out of this solid, right? It's measuring the extent of outflowingness of a vector field over this solid. But then flux is measuring like net rate of flow through some surface, right? And well, if this surface is the boundary of a solid, it makes sense that integrating the flux, right, or calculating the flux, which is calculating how much, like the rate of flow through this solid, it makes sense that this is the same as the solid on the inside, its tendency, the vector field over the solid, its tendency to flow out, right? And so it's like you're viewing this outflowingness, it's like whatever is leaving the solid E is passing through the surface S, right? And so integrating these quantities should be the same. And that's the intuition here, is the rate that things are flowing away from the solid E is also the rate in which things are flowing through the surface S. And that is the entire idea of the divergence theorem here, right? And so we can make that like remark in words. The rate at which a fluid, so let's say like F is representing like movement of a fluid through space, right? The rate at which a fluid leaves E is the same as the rate at which the fluid flows through S, because S is kind of like a gate, right, that separates E from everything else, right? And so the rate at which things are flowing out of E must be the same as the rate of things that are flowing through S, since this is like the only way you can leave E is to go through this gate that we're calling S here. That's this boundary surface, right? And so this gives us hopefully an intuitive idea along with the rigorous understanding of the divergence theorem. So with this, let's do an example. So let's calculate the flux of a given vector field F, where S So where the surface we're looking at is the cylinder, x squared plus y squared equals 1, and z is between 0 and 2, and f is the following vector field. We have 1/3 x cubed plus yz, 1/3 y cubed minus sine xz, and then we have z minus x minus y. Okay, and so we're looking at a cylinder of radius 1 and height 2, right? And so this cylinder is going to include the tops and the bottom. So like it's a Pringles can with a lid on it, right? And we want the surface integral, the vector surface integral of this vector field over the cylinder S. And this would be complicated to do without the divergence theorem, because you would have, this is piecewise smooth, right? So you would have to calculate like f dot ds is, you'd have to break this up, right? Because there's 3 regions to look at, right? Or there's 3 pieces of your surface. There's the top, there's the bottom, and then there's the shell that goes around, right? You have to think about these surfaces. Well, these are all parameterized differently, right? And so you'd have to set up 3 vector surface integrals to calculate what the total flux of the whole cylinder is, or the total flux of the vector field over the entire cylinder is. And so because of this, we can use the divergence theorem, because a triple integral over a cylinder is going to be much easier to calculate. And so let's use the divergence theorem here. The divergence theorem says that that the flux integral, or the vector surface integral, is the same as the triple integral over the solid, so now containing everything inside the cylinder, of the divergence of our vector field dv. And so we need to understand what E is, and we need to calculate the divergence of F. So first, let's write what E is going to be. Well, E is going to be, this is a cylinder, right? So it would make sense that we set this region up in cylindrical coordinates. And so E is a cylinder. Well, we have x squared plus y squared equals 1. And we want everything, including the interior. This is a solid cylinder now. E is the solid cylinder, right? And so in cylindrical coordinates, x squared plus y squared equals 1 is to say that r equals 1. And this is as far out as we can be, right? The shell is like the outer bound for our radius, and the z-axis is the inner bound. Well, the z-axis is a radius of 0. And so because of this, we want points r, theta, and z such that, and we can see we want r between 0 and 1, right? Because this is the radius for, or this is the bounds of the radius for a solid cylinder, where the outermost, where the shell of this cylinder is radius 1. We're sweeping around the entire cylinder, so that means theta is unrestricted. So it runs from 0 to 2 pi. And then we have a height of 2, right? Z is unchanged when you convert to cylindrical coordinates. And so that means we have Z between 0 and 2. And so this is now a nice description of our region E in cylindrical coordinates. The next thing we need to do is calculate the divergence of F. So, well, let me record on this page what F is again, so it's more clear to see. This was 1/3 x cubed plus yz, 1/3 y cubed minus sine xz, and then z minus x minus y. Okay, to calculate the divergence, remember the divergence of F is the gradient dot f. So this is d dx of 1/3 x cubed plus yz plus d dy of, because remember, the gradient is the operator expressed in vector form, del x, del y, del z, right? So this is d dy times, or of, excuse me, because this is an operator. So when we take the dot product, we think about like applying the operator to f. And so this is 1/3 y cubed minus sine x z, and then plus partial derivative with respect to z of z minus x minus y. Okay. Taking the partial derivative of the first piece with respect to x, well, it looks like we're going to get x squared and then plus y squared plus 1, right? Awesome. So now we have the divergence of f, and we've calculated this region E in cylindrical coordinates. So what's the divergence of E in cylindrical coordinates? X squared plus y squared is equal to r squared. So in cylindrical coordinates, the divergence of f is r squared plus 1. And now we can use both pieces of information here. We have the divergence of f in cylindrical coordinates, and we have the region E in cylindrical coordinates. And we have everything we need now to set up this triple integral. And so the flux integral of f over this cylinder S is, thanks to the divergence theorem, the triple integral over our region E of the divergence of f dv, which is, we learned E is the region where r goes from 0 to 1, theta goes from 0 to 2 pi, and z goes from 0 to 2. And the divergence of f we learned was r squared plus 1. And then remember, dv in cylindrical coordinates is r, dr, d theta, dv, or dz, not dv. Right? If you remember back to when we were studying triple integrals first, we learned that the differential dv is different depending on the coordinate system you're in. And we learned that if it's in cylindrical coordinates, it's r times dr, d theta, dz. And so we can calculate this integral here to calculate the flux. Well, if we integrate from 0 to 1, we get, so I could distribute this r, and it would become r cubed plus r, right? So after integration, this would be 1/4 r to the 4th plus 1/2 r squared from 1 to 0 d theta dz. Z equals 0 to 2, theta equals 0 to 2 pi. Well, if we plug in 1, we're going to get 1/4 plus 1/2, which is 3/4, right? And then if we plug in 0, we get 0. 3/4 d theta dz. So this is going to be integral z equals 0 to 2. If we integrate with respect to theta, we're going to get 3/4 theta, and then we would plug in 2 pi, right? So this is going to be 3/4 times 2 pi d z, which is then 3/4, because now we're going to integrate with respect to z, and then integrating with respect to z would be all of this constant here times z evaluated at 2 and 0. And so if we plug in z equals 2, we'll just take this whole quantity times 2, which means we would have 3/4 times 4 pi, which simplifies to 3 pi. And so here was a statement and understanding of the divergence theorem, along with a very standard example about how, okay, well, a certain surface integral may be relatively complicated, but thanks to the divergence theorem, we can just look at the triple integral over the region that this surface encloses and just set up a standard triple integral from there. And once we've done that, the integration is hopefully not too terrible. All righty. So this wraps up our Calculus 3 course for the summer. We've talked about a lot of topics from all the way back to just how to write things in parametric and polar coordinates to now in just 8 short weeks, we are looking at these pretty complicated and involved theorems of vector calculus. And this, throughout the semester, I hope that you've seen how all the different ideas of multivariable calculus, and also how important and often they are applied to other STEM disciplines, such as physics and engineering. Those are usually the most apparent. There are applications to like biology and chemistry even. So this wraps up the course. Thank you all for your time and willingness to study the subject of math with me.